Hello viewers, welcome back to my channel, and in this video we are going to talk about principle of mathematical induction. This is a topic in algebra, so kindly subscribe, then follow the video to the end so that you get deeper understanding, since you are going to solve several examples under this. Now let's see. Prove the statement for n equals 1. Now, that is the first point in the principle of mathematical induction. When you say principle of mathematical induction, it's a proof method in which we use to find the validity of mathematical statement for all natural numbers. So first of all, in order to do that, you have to prove that the statement is true for n equals 1. Because if you want to prove for all numbers, and even if it's not valid for when n equals 1, then you have to stop. So your base case should always be true before you proceed. Then the second is to assume that the statement is true for n is equal to k, where k is any positive integer. So this is what we call the induction hypothesis. It's very important. So you assume that the statement is true for n is equal to k. Then for the test part, you say from the assumption in 2, you prove that the statement must be true for n equals k plus 1. And this is also the difficult part of it. So here you base on the assumption, then you prove that the statement is true for n is equal to k plus 1. So we should quickly move and solve several examples so that you get deeper understanding. So kindly watch the video to the end. So in our first example, we have a problem here. It says 1 cube plus 2 cube, then plus 3 cube plus plus n cube is equal to n squared multiplying n plus 1 all squared all over 4. So this is our first example in this tutorial. So first of all, I said you have to find or test for when n equals 1. That's the base case. So for our base case, we are going to have, for n is equal to 1, the left hand side we are going to get 1 cube, and it should be the same as our right hand side, which is 1 squared multiplied by 1 plus 1 all squared over 4. From here you get 1 cube to be 1 on the left side. Our right side we are going to get 1 multiplied by 2 all squared over 4. Then we move on, you get 1 to be equal to 2 squared is 4, it will cancel, you get 1. Therefore our base case is true. Therefore we can proceed to go on with our proof method. So let's use our induction hypothesis and also assume that the statement is true for n is equal to k. So we are assuming n is equal to k is true. That is the assumption. We are going to have 1 cube plus 2 cube plus 3 cube plus plus n cube, plus k cube. Wherever you see n, you put k, is equal to k squared multiplied by k plus 1 all squared all over 4. So at this point, we are assuming that this statement is true, and that is the induction hypothesis. So let's move straight to our inductive step, where we have to prove. So proving n is equal to k plus 1 is true. Proving n equals k plus 1 is true, we are going to have 1 cube plus 2 cube plus 3 cube plus plus k cube, then plus k plus 1 all cube. When you say that when n equals k plus 1, you are not going to put only k plus 1 here. It's a sum of a series. So here is the kth term, so plus the k plus 1 term. That's why we had plus k plus 1 all cube. And this should give us k plus 1. Wherever we see n in this, we put k plus 1 straight away, all squared, multiplying k plus 1, then plus another 1 inside, all squared all over 4. So we have to show that the left hand side and the right hand side are equal. Then you see that our inductive or our statement is true for all natural numbers. So let's see. From here, we know that 1 cube plus this up to this side is the same thing here, and it's equal to this. So we bring this here as a substitution. So we remove this place and replace it with k squared multiplied by k plus 1 all squared over 4 plus k plus 1 all cubed to be equal to k plus 1 all squared multiplied by k plus 2. That is, I'm simplifying this place, all squared over 4. So you have to show that the left hand side and the right hand side are equal. So from here, I'll multiply this by this as we do with normal algebraic expression. K plus 1 all squared plus 4 k plus 1 all cubed all over 4 should be equal to k plus 1 all squared. When I simplify this, I'll get k squared plus 4k plus 4 all over 4. So when I come here to, I'll simplify, or I'll make k plus 1 the all to the power squared the subject. So I get k plus 1 all squared out. Then here I'll be left with k squared plus, here I'll be left with 4 open bracket k plus 1. All this over 4 is the same as k plus 1 all squared multiplying k squared plus 4k plus 4 all over 4. So at this point here I'll get k plus 1 all squared, k squared plus 4k plus 4 all on 4 to be equal to k plus 1 all squared multiplied by k squared plus 4k plus 4 all on 4. Since my left side and my right side are equal, I'll see that my mathematical induction or my inductive approach is valid. Therefore, this statement is true. So our inductive approach is now tested, and you have seen that the statement is true. Whenever you have 1q plus 2q plus 3q plus dot 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 to n cube, we can conclude that it's equal to n squared plus n plus 1 all squared over 4 for all natural numbers. Now let's go to the second example. So in our second example here, we are going to talk about this one. So this show that n cubed plus 2n is divisible by 3. So this is another form. So for mathematical induction, it doesn't follow one order. We have different ways depending on the question given. So here, this is a divisibility example. So in this example, we follow the same process. You prove our base case. That is our base case. When n is equal to 1, we are going to have 1 cubed plus 2 multiplying 1. And this will give us 1 plus 2, which is the same as 3. We can see that 3 is divisible by 3, therefore base case is true. Our base case is true. So once we have our base case to be true, we quickly move to the hypothesis. Now, before we do the hypothesis, we will assume, or we will let n cubed plus 2n to be equal to 3 multiplied by, let's say, L. We are making this because we are saying that this one is divisible by 3. So to prove that this is divisible by 3, we have to equate it to a multiple of 3 by a variable. So having 3L means 3L is divisible by 3 since it's a multiple of 3. So here we do our assumption. So assuming n is equal to k is true, I'll have k cubed plus 2k to be equal to 3L to be true. So I have assumed that k cubed plus 2k is equal to 3L. The 3L standing there means that it is divisible by 3. Now let's move straight to the proving for n equals k plus 1, the inductive step. Wherever I see n, I put k plus 1. So I have k plus 1 all cubed plus 2 multiplied by k plus 1. So here I have an expansion, a binomial expansion. I get k cubed plus 3k squared plus 3k plus 1. Here will be 2k plus 2. So from here, I'll factorize, or I'll group here k cube plus 2k at one side, this 2k, so that I can make reference from the assumption. Then plus 3k squared plus 3k, then I have 1 plus 2, which is plus 3. So at this point, I know that k cube plus 3k is the same as 3l. That is 3l from our assumption. So this is the same as 3l. So plus 3 open bracket k squared plus k plus 1. So we can see that 3l plus 3 this, they are all divisible by 3. Therefore, our statement is true. So we can see that n cubed plus 2n is then divisible by 3. So let's go to our next example. And in this example, it is using the inequality combined with the factorial. So it says that we should prove that 2 to the power n is less than n factorial for n greater than or equal to 4. So here, if you prove, so they are saying that for n is greater than or equal to 4, we have to prove that 2 to the power n is less than n factorial for n is greater than or equal to 4. So let's see here. From here, for the base case, we are not going to start from n equals 1 because they said for n is greater than or equal to 4. So let's see, using 4, I'm going to get 2 to the power 4 is less than 4 factorial. This is the same as 2 to the power 4 is 16 and is less than 4 factorial is the same as 24. So we can see that yes, it's true. Our base case is true. So therefore we can proceed to prove the statement above. So base case is not normally also when using n equals 1. It depends. So from here you can see that the statement made a condition that for n is greater than or equal to 4. So let's see what we have to do next. So we move to our assumption. For n is equal to k is true. That is our assumption, that when n equals k is true. So we have 2 to the power k to be less than k factorial. K factorial. Then we say that this statement is true. So in mathematical induction, you have different ways of doing it, but make sure that whatever way you took or whatever way you take, is the right approach, and you end up getting your statement being true. So here 2 to the power k is less than k factorial is our assumption. So this is our induction hypothesis. So this is true. Now let's see, for n is equal to k plus 1, I'll get 2 to the power k plus 1 less than k plus 1 factorial. So at this point, I'll further simplify to show that indeed this side is less than this. So how do we do that? So here is the same as 2 to the power k multiplied by 2 from indices is less than k plus 1 factorial. Now let's see, from our hypothesis, so from the assumption, let's see, 2k is less than k factorial. If I multiply left side and right side by 2, I'll get 2 multiplied by 2k, 2 to the power k is less than 2 multiplied by k factorial. So I can see that I'm getting this expression also here, and I'm seeing that this expression is less than this. So now let's see, from the assumption, this is true. This whole expression is less than this. From the assumption, this is less than this, and it's true. So we have to show that this is less than this. That is the inductive step that we are doing. That is what we are supposed to prove. You have to prove that this itself is less than this. But from our assumption, we can see that this is less than this from the assumption, which is true. So now let's see to prove this. Let's see how we will do it. And to do this, you have to show that this one is less than this, so that we can see that if this one is less than this and this one is less than this, then this one is indeed less than that. So from here, let's see something here. We can see that if you have 2 multiplied by k factorial is the same as 2 multiplied by k. If you have a factorial, is the same as k multiplied by k minus 1 factorial. That is for this part. So from here, let's see for this one too, k plus 1 2. So k plus 1 all factorial is equal to k plus 1 multiplying k. The reason is if you have any number factorial, it's the same as that number multiplied by that number minus 1 multiplied by that number minus 2. So k plus 1 multiplied by k plus 1 minus 1, that will be k. Then finally multiplied by k minus 1 factorial. So we can see that k plus 1 all factorial is the same as k squared plus k multiplying k minus 1 factorial. So from here, this is greater than this, because we have this factorial, the same thing here. But here is 2k and here is k squared plus k. So we can see that this is greater than this. So from our assumption, we can say that 2 open brackets k factorial is less than k plus 1 factorial. That is from here. We can see that this one is less than this, because this is less than that, but here and here are equal. So if this one is less than this, and here we saw that 2 multiplying 2 to the power k is less than this. So this is less than this one from our assumption, which is true. Then also this one is less than this. Then automatically 2 to the power k multiplied by 2 is also less than this. Therefore, you say that 2 multiplied by 2 to the power k is also less than k plus 1 or factorial. Therefore, our statement has been proved. So this is a way we go about it. We have to show that this thing was less than this. But we realize that from our assumption, 2 to the power k multiplied by 2 is less than this. So we can compare this and this, then also use that for our assumption. That's what we did. So from here, we saw that this gave us this, then the k plus 1 gave us this. Therefore, this is less than this. Then if this one is less than this, and this one is also less than this, then this one is less than that. You can even use some of the raw numbers theorem to see that if I'm less than you and you are less than somebody, then I'm automatically less than that person. So this is the end of this question. So